Okay, good afternoon. So we have two more lectures before the midterm, and the exam will cover all the materials that we taught until this Thursday. I mean, this week's material will be included in the midterm exam. Okay. But what we are going to do this week is relatively simple in the sense of we are going to just try to apply what we just learned in last week, so the basic principles of statistical mechanics, to simplest independent particle systems. Okay, and so we will focus on a few things. Today we will talk about independent spins, and then this idea of partition, or this idea of separating independent systems into smaller subsystems, and they use the subsystem partition function to obtain this many particle partition function for independent particles, independent systems. Okay, and then I think on Thursday we will be able to cover the principles of applying all these rules to classical systems, which contain continuous variables instead of state. We would need to describe systems using continuous variable. And in that case, the rule still apply, but you need to kind of change how we calculate things a little bit. Okay, so including basic applications will be the topics of this week's lectures. So let's review. So let me share my iPad. So let's begin by review, please.
Can you hear me? Sorry, do you
Yes.
hear me? Okay.
Yes.
Which point dropping? But I want to ask, the exam would be open book or the closed book?
Closed book. Yes.
So because some of us, like students, are taking the class for the first time in our
Yes.
academy, so it's kind of difficult for us. So we were like, we wanted to talk to you, but we didn't. So we were worried about our mids and our finals. So, or can you tell us what kind of like
the exam will be very similar to what you found in your homework, but maybe even easier. Okay.
All right. Yeah. So we're really like.
And don't worry about if you need to memorize anything. There's no need to memorize anything. Any equations that will be used in the exam which cannot be derived, or which are, I feel that you would need to use those equations. It will be provided.
All right.
So today I'm going to teach you, or I'm going to use Stirling's formula. For example, right. Today I'm going to use Stirling's formula, and Stirling's formula will be provided in the exam.
Oh, all right.
Okay, so there's nothing that you can gain by take a look at the book. Actually,
thank
an
you.
open book exam will be much more difficult. We don't want that.
Sure, sir. Thank you, sir.
Yes. Okay. Any questions about the exam, or about anything? Anything? Again, you can still send me email to arrange for an appointment this week sometime, or even next Monday. Okay. So if you want to ask questions, if you want to, you want me to help you clarify some of your ideas, then shoot me an email. We will arrange a time slot for your office hour. Okay. So the most important results we obtained in last week's, considering ensembles. So we discussed a few ensembles. We talk about when we fix energy, volume, and number of particles, which gives the canonical ensemble. A canonical ensemble, every microstate has the same energy, so its probability of occurring is the same. And the entropy, which is the key thermodynamic function in this ensemble, can be calculated from the number of microstates. So this omega here is number of microstates in this ensemble that satisfies the same energy, the same volume, and the same number of particles. And in this case, thermodynamics tells us that ds equals to 1 over t times dE plus P divided by T times dV minus T mu dN. This is not from static, this is from thermal. From the fundamental equations of thermodynamics. By comparing these two equations, mathematically, we know that the total derivative of entropy in terms this equation, total derivative of entropy, tells us a lot of things that connects this entropy formula with thermodynamic variables. For example, 1 over T or 1 over kBT can be calculated from taking the natural log number of states, partial derivative of it with respect to energy at fixed volume and so on and so forth. So 1 P over T is partial natural log omega partial V minus mu over T is partial natural log omega partial N. So I don't need to write them down. But because this microcanonical ensemble is constructed with fixed energy, which is not something easily performed experimentally. So it's more useful if we consider an ensemble with fixed temperature instead of energy, volume, and the number of particles. And in this case, you have a canonical ensemble. And now the energy can fluctuate. This entropy has to calculate it from Gibbs entropy formula. So this entropy now is divided by kV and some average over all the expectation value, all the microstates, expectation value of natural log P nu over all the microstates. That's the entropy, Gibbs entropy. And with this formula, we know that this probability Boltzmann distribution actually is 1 over Q exponential minus beta E nu is determined by the energy of the microstate. And this Q here is the canonical partition function, which is the sum over all the microstates exponential minus beta E nu. This tells us that as long as you know the energy of all the states, actually this has to do with energy of all the states, and this is actually the spectrum. As long as you know the spectrum of the system, then you can calculate canonical partition function. And then with canonical partition function, one can calculate the Helmholtz free energy. So A is minus kBT, natural Q. We show this. And with Helmholtz free energy and this total derivative of Helmholtz free energy, dA equals to minus SDT minus PdV plus mu dN. One can then calculate everything like entropy minus S will be partial A partial T at fixed V and N, for example. Okay. So this allows us to calculate all the thermodynamic functions and thermodynamic variables from microscopic canonical partition function. I didn't talk about grand canonical ensemble in the class, but I provided a note about this in NTU Cool, on NTU Cool. Okay. Interested students can take a look, but you don't need to actually know how it's derived. You only need to know that we can furthermore lose or reduce the constraint we applied on this ensemble. We can consider an ensemble in which the number of particles can fluctuate, the number of particles can change. Okay, this is actually a very natural setting for chemical reactions, because for chemical reactions to happen, for chemical equilibrium to exist, you need particles, you need chemical species to exchange with each other, right? You need chemical reaction to happen, which turns one type of particles into another type of particle, or even disappear. So number of particles can change. It's no longer a fixed number. But in that case, we, instead of fixing number of particles, we fix chemical potential. So in that case, you operate in an ensemble with fixed temperature, fixed volume, and fixed chemical potential. And this is called grand canonical ensemble. Seems like it's more general. Number of particles can fluctuate. However, in thermodynamic equilibrium, actually fixing chemical potential also fix number of particles. So either one is the same. All the ensembles are the same. Yeah, we already demonstrated that microcanonical ensemble and the canonical ensemble at the large system size limit, large n limit, both ensemble converge to the same result, because this change of number of particles, the number fluctuation is just too small to be measured. So they are equivalent to each other. So in grand canonical ensemble, this entropy still follows this Gibbs formula. And the key here is that we need to introduce a new variable into our probability distribution, which is the chemical potential. Now, chemical potential is the probability depends on chemical potential. So this probability now is 1 over psi. Use this. This is the notation used by Chandler in his book. So I use this xi Greek character to represent this grand canonical partition function. It's right here. Grand canonical partition function. Okay. And now this probability depends on micro minus beta E nu, as well as the actually is total chemical potential. So it's minus is n nu beta, so beta n nu. N should, I should say, beta mu. Mu is a chemical potential, and the number of particles in this microstate, n nu microstate. And you can easily see that this actually is exponential minus beta. So now your E nu minus mu and nu. So now the energy, originally in canonical ensemble, you have a single energy turn, but this energy turn now became an energy turn plus an energy shift. So this chemical potential corresponds to an energy shift. So this chemical potential turn actually is a reference system turn. It depends on how you define your reference energy, and this is called chemical potential. This is some sort of a reference, E, F, E, R, E, N, C, energy. This this chemical potential is actually a reference energy in this probability distribution. And as long as you calculate this grand canonical partition function Xi, you can calculate thermodynamic properties using this connection. PV, P is the pressure times volume, equals to equals KVT. KVT, it must be positive, so KVT natural log Xi. Okay, so your grand canonical partition function, take natural log multiplied by KVT will give you P and P times V. Okay, and this also provides a connection to thermodynamic properties. So from this equation and the fundamental principles of thermodynamics, you can calculate all the thermodynamic variables from this equation using this grand canonical partition function. Later on, we will use this result. We'll use this result, this partition grand canonical partition function. We will utilize this. But I don't need to provide any derivation as long as you kind of get the physical picture of this equation, this probability here. So our next task will be to apply those rules to simple systems to demonstrate how those very concise principles could be utilized to calculate experimental observables. So for this case, for this purpose, to this end, we will consider a very simple case first. We will consider independent spins. And actually, when we talk about spins, we say spin 1/2 systems. Any spin 1/2 system is a two-level system. Normally, in quantum mechanics, we'll use alpha spin, beta spin to denote the spin of an electron. But actually, alpha, beta are the respective spin states of a spin 1/2 particle. So there are two states in this spin degrees of freedom, and this is fundamentally a two-level system, an intrinsic two-level system. It also exists many two-level systems playing very important roles in our everyday life in describing all sorts of physical phenomena. Okay, for example, for a molecular system, if we want to describe its excited state dynamics, and we want to describe its UV visible property absorption, normally we consider ground state and the first excited state of a molecular system. Okay. And in this case, if your laser, if the photon you consider are in the energy neighborhood of this ground state to first excited state transition, normally this ground state to second excited state, ground state to higher excited state transitions would not occur in your experiment. And you can just ignore all those higher excited states and only consider ground state and the first excited state. Okay. In this case, you also need to consider a two-level system, but this time this two-level system is truncated two-level system. Original Hamiltonian has more states, more than two levels, but the energy range you consider, the physical phenomena you are interested in, only concerns these two levels. Then you reduce to a two-level system. Okay. What I'm trying to say is, two-level systems are actually intrinsically a very important system in many physical and chemical phenomena. So we have n independent spins. To be more specific, we consider n independent spins. So n spins. This tells us you have n two-level systems. N spins. And two-level system TLS. Okay, two-level system. Of course, TLS, two-level system. And for simplicity, we will first consider those two-level systems as independent. Independent means their energy, entropy, all sorts of variables are additive. So this tells us that it's the total Hamiltonian. Yes. System 1, system 2, system 3. And total energy will be energy, first spin energy, second spin energy, third spin. This is what independent means. When you consider the two spins, it's just additive of two single spins. And then we consider they are distinguishable. UISHABLE, which means we can assign labeling to it. 1, 2 are different. So we can recognize different. And this is most easily done on a spin lattice. Spin lattice means you have an array of spins organized in a regular way, that you have a well-defined unit. So you can construct the whole system with repeated units. In that case, we say you have a lattice. So graphically, we can consider this as you have spin 1 to label, spin 2 to label, spin 3 to label, You have more than spin n to label. So this first spin, second spin, third spin, nth spin. You have so many spins. And in this case, but this part is not necessary, but in this case, we will assume the energy difference from the ground state and excited state of each spin is the same. So we assume that this energy gap here is S. So this S is energy gap. And now for each spin, it can either be on the ground state or on the excited state. We have only two states, so ground state, excited state, low energy state, high energy state. And for simplicity, we will consider the ground state to be state 0, excited state to be state 1. This is just it is a labeling. It is not necessary being 0 or 1, but the why I use this will be apparent right away. Okay. So a microstate is denoted now by a vector. And this vector tells us either the first spin is in the ground state or first state, second spin, third spin, so on and so forth. So you have an array n1, n2, n3, and n. Okay. And each ni can be either 0 or 1 in 0 or 1 state. It's either 0 or 1. It cannot be any other value because we just have these two different states. Okay. And choose 0 or 1 is convenient to calculate total energy. So the total energy over this microstate is now sum over ni times S. So if it's 0, then it's on the ground state, we define this as energy 0, reference energy, reference point. And if it's in the excited state, you will have an energy action. Energy action. And then add them together, you have this total energy. Okay. So this kind of notation of using 0, 1, and 0 means ground state, 1 means first excited state. And you can actually go further. You have a 3-level system, 4-level system. Then you can have a 0, 1, 2, 0, 1, 2, 3, for example. And this is actually called the occupation number. Occupation number representation. So this is an occupation number representation for less independent distinguishable spin systems. And it's very convenient. Later on, we will use this even more. So we know how to calculate energy. In principle, then we can calculate partition function. Partition function are sum over all these things, right? Okay. But recall that in this case, you have n different spins. So there are how many microstates are there? Yeah. How many? Each spin can be either 0 or 1, 2 possibility. You have an n spin. So there are 2 to the n states. So say micro states. So now we want to calculate. Entropy, for example, entropy of the system, or the average energy at a given temperature of a system. Okay, those are thermodynamic variables that we want to calculate. And with this information, with this model, we can already do that. And we can do that in different ways. And I'm going to show you to calculate the average energy at a given temperature using different approaches. Okay. So the first approach, we will use a microcanonical ensemble. So microcanonical ensemble fits A, V, N. Number of particles is already fixed. We have n spins. Okay, so it's fixed. It's fixed. Volume, there's no volume in this case, so it's fixed. And we need to fix energy. And we know that for a given energy E, each spin has an energy epsilon, right? If we excite one spin, you get small epsilon energy. So to get total energy E, you need to excite E divided by epsilon energy. So total number, total number of excited spins. So you have many spins, but within those so many spins, you have E divided by epsilon spins are excited. Total number of excited spin, and then total number n. Right. So for simplicity, I'll call this small m. Small m. So you have m excited spins, but you have n total number of spins. So out of those n spins, you need m spins excited. And what are the combinations, number of combinations in this case? It's easy to calculate, right? And this number of combinations is the number of states. Is this omega E and n? Actually, will be n choose m. you have n spins. Out of those n spins, you need m of them occupied, right? N choose m. N choose m. And we know how to calculate n choose m. N choose m is n factorial divided by m factorial and n minus m factorial. So in this case, it's easy to calculate the number of states in a microcanonical example because the spins are the same. The actually is energy content. The energy content is known and easy to do. And for this to be applicable, we need this energy to be a large number. We also need this n, this number of spins, to be a larger number, corresponding to the thermodynamic limit. Okay, which should not be a problem. So what's the next step? Let's go back. We begin here. Next step, we should calculate entropy. So entropy, according to Boltzmann's formula, so entropy can now be calculated as Kb natural log omega. So it will be Kb natural log n factorial minus natural log m factorial minus natural log n minus n factorial. And this factorial is quite troublesome because it's a large number and it's not easily calculated. Actually, even in a computer, this calculating this n factorial exactly is not a simple task. But anytime you see a natural log n factorial and this n or this m, both are large numbers. So natural log factorial of a large number, you should apply so-called Stirring's formula. So I'll give you the Stirring's formula first. So it's let me put it right down as a box. Stirling formula. Very, very, very important mathematical result. That tells us natural log of some factorial is actually, it can be approximated by m natural log m minus m. And the requirement for this is large n. For any large number, how large is called large? Actually, 50 or 100 is large enough. So it's for the n spin that we consider here is in the 10 to the 23 order of magnitude. It's large, is very it's very enough. Let me say this. So Stirling's formula, applying on those large numbers, provides very excellent approximation for natural log m factorial and also n factorial, for that matter, n factorial, m factorial can be calculated. So we'll use Stirling's formula to expand. M factorial became n natural log n minus n. M factorial became m natural log m minus became plus m. So you have this minus sign here. Okay. N minus m factorial will be n minus m natural log n minus m plus n minus m. Okay. So you see, now this n cancels out. This m cancels out. And we'll keep it here. Let's collect the terms. So this became v n natural log n minus m natural log m minus n minus m nature log n minus m. So next thing we want to do is to calculate some thermodynamic variable. Okay. And so what can we calculate? We want to know the temperature. Want to know the temperature, right? Yeah. So how can we calculate temperature? By partial natural log omega partial E. Partial natural log omega partial E. So one over T inverse temperature will be partial S partial E at phase n in this case. Phase n is actually large n, so number of particles, number of spins, total number of spins. So partial S partial E, we have this. We have this. So E is m echelon. So partial E actually is echelon. Echelon is a constant, so partial m. Partial m. So this will be 1 over echelon. This partial E here, you have an echelon m. Echelon is constant. So you have a partial S, partial m. Is n. So we know how to do this here, right? Okay. So let's do it. So this will be KB divided by echelon times this n natural log n10 goes away, minus m natural log m10. You need to take derivative of the first term and then the second term separately. So when taking derivative of the first term, partial m, you have the minus natural log m. When taking derivative of the second term, natural log m gives you 1 over m, and multiplied by m, it became 1, so minus 1. Same applies here. So you have a minus n minus m will give you partial m minus m. So actually you can do this by yourself, right? Yeah. It's very not inconvenient for me to do this. So n minus m. We'll take derivative of this first. That will give us n goes away minus m. Take derivative with respect to m, give you 1 minus 1, so plus 1. Plus nature of n minus m. And the second one, you will have negative minus m minus 1, so plus 1. So you take derivative over this. Apply chain rule, so you have 1 over n minus m first, which cancels out with the n minus m in front of it to give you minus 1. And then you need to take derivative of n minus m, which gives you minus 1. And you have a, in total, minus plus 1. So this goes away. So what we have here is 1 over t became, let me see, nature log n minus m divided by m. Kb divided by kb divided by echelon times nature log n minus n. N minus n. X. Not very difficult to calculate, actually. So I will put this KBT here, KB here to become KBT, and 1 over KBT will be beta. So beta equals to 1 over epsilon. Then you have a natural log m n m. And let's go back here. M is actually related to epsilon and your total energy E. I want to change this back to energy. Let's do it. Let's do it this first. So you have this, then you have epsilon beta epsilon. So we have n divided by m minus m equals to exponential beta epsilon. We calculate m.错了，减一，对 ，yeah. You see, it's very easy to make a mistake, but somehow I know I made a mistake already. Yeah. Of course, this is minus 1, minus 1, minus 1. So n divided by m is exponential beta epsilon 1 plus this. So m is you inverse, you take the inverse of this m n times 1 plus exponential beta epsilon. Okay, yes. Yes. And this is m. M is actually E divided by epsilon. So let's plug this in. So E divided by epsilon is n 1 plus exponential beta epsilon. So your energy, internal energy, can be calculated. It's a function of your epsilon and temperature. It depends on n and temperature. So it's a function of n. I should use T and n. That's how I define this. T and n. Those are two thermodynamic constraints you have on this system. And it will be n epsilon divided by 1 plus exponential beta epsilon. So this is the average energy. And now you see that this average energy of a system depends on the temperature. When temperature increases, this energy will, when temperature increases, beta decreases. So the energy will increases. So when this tells us that when T equals to 0, when temperature goes to absolute 0, this beta epsilon became a very large number. So you have an exponential very large number down there, and your energy will approach 0 quickly, actually. So this means every spin is in its ground state, all in ground state. This is a state, all in ground state. And when temperature increases, energy increases. And then when temperature goes to infinite, your beta goes to a very, temperature goes to infinite. Beta is 1 over kBt, it approaches 0. So you have an exponential 0, which approaches 1. So in that case, you have your energy will be n epsilon divided by 2. this actually means half of the spins are in the ground state and half of the spins are in the excited state. Half, and which actually is a half totally random distribution. All microstates have the same probability at infinite temperature. And since E is fixed at a given temperature, so your energy is fixed at a given temperature in this formula, of course. So given N, given temperature, you know the energy. So you have some thermal averaged energy in this case. But recall, we actually derived this equation from microcanonical ensemble. We assume fixed energy ensemble. But in the result, we can connect this to thermodynamic variable. And then we know when you vary the temperature, how the energy changes. So in the thermodynamic sense, the energy is no longer, we do not constrain on a single energy only, actually. We actually clearly found the average energy at different temperatures. Okay. So this is a simple case in microcanonical ensemble. And what if we choose a different ensemble to do the calculation? We can use a canonical ensemble. To do the calculation. So in this case, actually, we need to calculate the canonical partition function, which is simply sum over all possible microstates, and exponential minus beta E nu. And each microstate is actually defined by an array. And each element in this array is either 0 or 1. So now the total energy can fluctuate. Total energy depends on those occupation numbers of that microstate, microstate. So we can then, what should we do? We actually sum over all the possible microstates. This will be sum over all the possible microstates exponential minus beta. Then this sum over E nu will be sum over I spin, and Ni for this microstate. So for each microstate, you have a different occupation number. You sum over all the microstates and sum over all the Nis. So you realize that sum over all microstates actually represents sum over all the combinations of Ni. Sum over all the combinations of Ni. So I will rephrase this right here. Sum over nu means sum over all summation all combinations of Ni. I will use this curved bracket to denote it. All possible Ni. So this means this sum over state in this case can be counted. We have a N1, N2, N3 to ... and capital N. Each one can be either 0 or 1. Each one can be either 0 or 1. So you select 0, 1, 0, 1, 0, 1, 0, 1, any combination. You have a set of this vector ni, and then exponential minus beta sum over, I use j equals to E1 to n, and j echelon. This will be the total energy. And we need to sum over all the possible nj's. All the possible nj, all the combinations are denoted here. And this is sum over n1, n2, each 0, 1. And this summation on top of exponential became multiplication. So j equals to 1 to n, and then you have the exponential minus beta and j echelon. So interpretation of here is this part gives you all possible combinations of ni, and with each combination, you then multiply this exponential minus beta n j epsilon together. And because this is the only possible combinations, we can now exchange this multiplication and this summation. This is only possible when you sum over all the combination. Okay. For that matter, actually all the permutations of the numbers. And since you sum over all the permutations, then how you multiply to get all those permutations doesn't matter. So this can be use normal color here. So this became multiply j equals to 1 to n for each spin. And then for each nj, it could be 0 or 1. And then you have minus beta echelon nj. Think about this. This is the most confusing part of this derivation, but this mathematically, this is sound, this step. And think about it, and we should take a break here just for 5 minutes, okay? Maybe we will come back at 2:20, 20 past 2. Think about if you, okay? So we should continue. Any questions? Anything? Okay, if not, then it means this is actually quite straightforward. So the next step will be simple. We evaluate the summation first. So this tells us you have multiply all everything. But this summation, for each nj, you have either 0 or 1. So it's just 2 terms. This summation is very easy to evaluate. So we have 2 terms. First term is nj equals to 0, and this exponential became 1. Exponential 0 equals to 1. The second term will be exponential minus beta epsilon. Just 2 terms. And now this term is independent of nj, or say independent of j. This is a simple consequence of that. For each ni, for each nj, n1, n2, n3, they have the same 0 and 1 terms to be summed up. So in the end, you have 1 plus exponential minus beta epsilon to the nth power. This is Q. And we want to calculate average energy. And this average energy can be easily calculated from partial nature log Q partial beta at this end, in this case, right? This average energy in canonical ensemble is calculated this way. So partial nature of Q, we have, let's calculate nature of Q first. Nature of Q is nature log 1 plus exponential minus beta epsilon to nth power. So take nature log of this, you have n nature log 1 plus exponential minus beta epsilon. Okay. So we take a derivative of this with respect to beta. We will have this n tandem plus minus n times nature log of this, then you have 1 plus exponential minus beta epsilon over 1 times we take derivative of since in there you have this one goes away, then this became minus epsilon exponential minus beta epsilon. Minus goes away, and exponential beta epsilon. I'll do it slowly. So n epsilon 1 plus exponential minus beta epsilon times exponential minus beta epsilon. So you multiply above and below by exponential beta epsilon. So you have this. I want to write 1 in front of this. 1 plus exponential beta epsilon and epsilon, and this will be your energy. Finish our calculation. Relate energy to temperature as well as number of particles, number of spins in the system. And let's go back to compare this with the result we obtained from the microcanonical ensemble. And it's not surprising that we have the same result, because those two ensembles give rise to the same thermodynamic state at any given temperature. And temperature determines average energy. This is the key. So with this practice, we demonstrated that you can choose either ensemble to do the calculation, but in the end you get the same result, because controlling temperature or controlling energy, in the end you reach the same thermodynamic state. So this agreement tells us that ensembles are equivalent. Okay. So you can choose the most convenient ensemble to do your calculation. Now we want to look at this result more carefully, actually. So if we plot E against temperature, so we want to see the average energy as a function of a temperature. And this equation tells us that this will very much like have a curve like this. And a very, very high temperature, it will be half n times epsilon. And start with 0 at 0 temperature. Then there is a region of a transition, smooth transition actually, like this, for this function. So So at a different temperature, the average energy increases. But not only that, the change or the distribution of energy actually also increases. Okay. And this is the essence of the temperature. At a higher temperature, you have a broader distribution of energy. At a lower temperature, you have a narrower distribution in the energy. It's fundamental in statistical mechanics. In thermodynamics, temperature corresponds to the fluctuation, the width of the distribution. Okay. So our next topic will be actually a third method to do this calculation. So we do this calculation using microcanonical number, canonical number. The third calculation that I am going to use is to use a single particle. Single particle partition function. Partition function. That is, since we are considering an n-independent electron case or n-independent spin case, so we have an n independent spins. So we should be able to calculate average energy of each spin and multiply that by n, because n independent. So if we can consider single spin, any quantity, any thermodynamic quantity, extensive quantity for a single spin should be able to be used to calculate the n spin quantity just by a multiplication of n. Okay, so single spin, if we calculate single spin and we have its energy, because we have this E already used, so let's calculate say spin number 1. So spin number 1, spin 1 with this energy. Then n spin, because they are identical. I didn't explicitly mention it's identical, but remember that we consider all the options are the same. So they are identical particles. Should be just n times E1. So for single spin, we have two states. First state energy is 0. Second state energy, the steady state energy, is epsilon, right? So for n spin system, we use capital Q. Here we use a small q. So small q will be very easy to calculate. Will be sum over this new now is sum over I is 0 or 1. Then exponential minus beta epsilon. So easy 1 plus exponential minus beta epsilon. So this is the single spin partition function. And single spin average energy We still call it spin number 1. So this average energy will be just minus nature log small q partial beta. Now there's no number of states. No number of particles to be fixed here. So just take this derivative. And we know how to take this derivative. We already know this q. So nature log q minus 1 plus exponential minus beta epsilon 1 times. You take derivative over the thing inside nature log is q, then you have a minus epsilon exponential minus beta epsilon. So you see something very familiar with what we calculated before for the n-spin canonical ensemble case, right? So we have an average E1 equals to epsilon here. Down there, you have a 1 plus exponential exponential epsilon beta epsilon 1 plus exponential beta epsilon. This is for a single spin. So n-spin energy, the real average energy, and this is for n-spins, will be this times n times n plus exponential beta epsilon. So you should not be surprised that previously when we calculate this using microcanonical ensemble, using my canonical ensemble, this structure here actually tells us that this q, this is here is multiplied by all the j, but each j here is what? J's spin. You go over all the spins and then multiply the single particle partition function together. Q equals to Q1, Q2, Q3, Qn. And they are all the same, so they are Q to the power of n. So you have this single particle partition function raised to the power of n, and you then obtain this n particle partition function. So this additivity in energy actually is governed or is given rise by this multiplicability in partition function. So your n particle partition function will be your single particle partition function multiplied Q2, Q3 together. And if they are the same, if they are identical particles, then it's the same partition function raised to the power of n. So this gives us a prescription of calculating partition function, n particle partition function from single particle partition function. This is very important result, and it's very useful. It simplifies the calculation a lot. So let's calculate n particle partition function. Particle here, of course, corresponds to a spin. So you will see that in statistical mechanics, this term particle is used very broadly to cover different state, to cover different component of a system. And in this case, a particle, each spin is a particle. Okay, so this particle is not this classical particle sense, but it's in the quantum mechanical quasi-particle sense. N particle or n spin partition function from single spin partition function. And this is valid for independent systems. And whenever you have independent systems, you should use partition function of each component to construct the partition function of the total system. Okay. And its multiplication actually is quite clear that partition function actually is utilized to count number of states in the system, actually. And for independent systems, number of states grows exponentially. Their number of states, likelihood of in each state actually is by multiplication. And this is why the total partition function is constructed from multiplications of individual partition functions. From single spin, single particle, let's use consistent terminology. And this allows us to calculate properties using a divide and conquer approach. So instead of consider a total spin states of a particular system, we can divide the system into subsystems, calculate dealing with independent subsystems individually, and in the end get the total system partition function by multiply all the partition functions together. So it's a product state, a product form. Okay. This rule can be further generalized to treat in addition to independent particles, to treat so-called indistinguishable particles. So for n in distinguishable, distinguishable particles, independent particles. Because indistinguishable, so they must be identical. D-I-D-E-N-T-I-C-A-L, identical. They must be identical. If they are not identical, then they are not indistinguishable independent particles. Then in this case, actually, because particles are indistinguishable, so your total partition function will be your single particle partition function raised to the power of n. But like I said, the partition function counts the number of states. But because they are indistinguishable, so all the permutation, you only consider combination. All the permutation should be considered as a single state. So you need to divide by n factorial. What I'm trying to say is, if we have a 3-particle system, and this configuration is exactly the same, what I'm saying is these 3 dots in this box are in exactly the same position. Let's use 4. Okay, 4. Exactly the same location. But if we have numbers on the particle, 1, 2, 3, 4, maybe different color, that would be distinguishable. 1, 2, 4, 3. 1, 3, 4, 2. 1, 4, 2, 3. What I'm saying is, in distinguishable case, they are same state. They have a different permutation, but in the end, they corresponds to the same microstate because you cannot distinguish those four configurations. And then because there are n particles, so we need to divide this by n factorial. This indistinguishable principle is actually nature in quantum mechanics. Because in quantum mechanics, you use wave functions to describe a particular state. Okay, and you cannot distinguish different electrons. You can only know the density of any electron at some location. On the other hand, in this case, this is distinguishable. And what does that mean? I will use the same 4 box. And actually, no need to use 4. I use 2 is enough. In this case, actually, each ball have different color. They can either be labeled or they can, if it's classical. Classically, it's nature that those particles are distinguishable. For example, if you have 4 ping pong balls, they are distinguishable. They are different balls, right? Okay. So either you have a color on it or no color on it, you can distinguish different ping pong balls. They cannot be totally fully identical. So in this case, actually, if each ball have different color, okay, and these 2 configuration would correspond to different states. They do not overlap with each other. So they are the same states. They are different states. They are different states, distinguishable. Or naturally, if you have a system that's arranged on lattice points, so on lattice, they are spatially separated and they do not move. Do not move. If they can move, that's a different story. But if they cannot move, they are fixed on lattice, then they are intrinsically distinguishable. Okay, because they are spatially separated. You can then have a number 1, number 2, number 3, number 4, number 6. This number 2 will stay there during the whole period of your experiment. You can clearly distinguish, look at number 1, look at number 2. But if these particles can move, then it's a different story. It's indistinguishable. So if you have a conjugated chain of electrons, now this electron can move along this chain. Then, like in that case, is indistinguishable electrons. Okay. So sometimes this could be confusing, especially for if you learn this subject for the first time. But this distinguishability is a very important subject. Very important. Before the dawn of quantum mechanics, this is actually not easily recognized. Because in classical systems, like I said, you have different ping pong balls. They are naturally distinguishable. You wouldn't imagine that the particles can be indistinguishable. You normally think distinguishability, particle, they are kind of indistinguishability, and particles, they are kind of conflicting terms. Because in our everyday classical world, particles are distinguishable. But in quantum mechanics, it's not so. So before this quantum principle was realized, scientists have a very difficult time to kind of understand this distinguishability phenomenon. Gibbs, when trying to derive the partition function and the ideal gas and the equation of state for an ideal gas system, was very confused by his result, because in the end his result has to be divided by this n factorial. So he need to use this case to derive PV and NRT. So this is needed. What I'm saying is needed to derive PV equals to Gibbs. But Gibbs found out that he couldn't derive PV equals to NRT with this principle, this distinguishable case. And at that time, he had no clue about how come this is the case. So it's called a Gibbs paradox. It confuses Gibbs for quite a long time. And in the end, Gibbs just arbitrarily plug in this 1 over n factorial factor to make the answer right, but he did not have a clue to explain. No, in the end, he knew it is about distinguishability. But without quantum mechanics, he cannot fully, what should I say? He could not fully explain this phenomenon. So this is a very important. I'm sorry? So this is a very important result, okay? And I think today we'll stop here. And next time we are going to talk about how we change this sum over state into integration over position and the momentum. I mean, we want to treat ideal gas system. So next time we will introduce this, we will study classical ideal gas, and then we need this classical formula to calculate partition function. And with that piece of information, we will complete everything we need or everything we want to introduce in this class about basic fundamental principles of statistical thermodynamics. So fundamental principles will be completed, and then we can shift to applications. So next Tuesday, a week from now, we will have our midterm exam, and the midterm exam will be held at the classroom. So I think we will assign the classroom 210 for this class, and it will be a in-person exam. So you need to come to the chemistry department, to the building, to do the exam. Okay, I'll stop here. Any questions? I'll answer that asymptotic analysis, this low temperature limit case next time. In the end, it should be very simple, but somehow I cannot get the the answer at this point. But next time, yeah, I'll show you how to do it. Okay. Okay. Oh, please.
老师，那个下一页。
Next, this one.
对对对。
Yes.
我拍个笔记。
Okay. So the key here is if particles are indistinguishable, then all those permutations corresponds to the same states. For a 4-particle case, actually there are four particles, 4 factorial such states. So in this case, Q to the power of n counts all the states differently, but we need to divide that by 1 over n factorial to count it only once. Okay? And this is required to derive PV equals to nRT. If you do not know this n factorial factor, you cannot properly derive PV equals to nRT. Okay. Any more questions? Okay, if not, we'll stop here and see you on Thursday.